So it is lecture number 16. Here we will talk about parameter estimation for generic linear model. That means what I told that we are having a regression function. Generally we are having a regression function. Either you can represent it f of x, you can call it, or simply uh, f of x happens to be hypothesis function, and we are defining it like this way, and expectation of that conditional expectation of y given x. This is the ultimate source of defining various model, whether it is linear model or non-linear model. If you are saying linear model, then the parameter would be linear in nature. So in short, we can say that we try to express like this way: W transpose some data, that features will come here. Simply I am writing like this way, or in short also you can write it data matrix like this way. That example we had taken, simplest linear one you are talking about. This the bold one is talking about data matrix times omega. That is the parameter, so that we are talking about here. The variable would be omega. Why? Because x would be given to you from the data. X would be given it to, so variable would be omega, and we see that this one is linear with respect to omega, so that's why it is a linear model. If it is not linear model, then you will see in neural network there is activation function. Generally it happens to be sigmoid or hyperbolic or something like that. So that time it would be g of some g of linear function. It is not like linear, you are not going to live anywhere. So sometimes linear would be explicitly in case of linear model, but for non-linear model it becomes function argument of the non-linear function g. There would be some non-linear function and where argument would be linear one. So that is the approach for any kind of probabilistic model to model any data set. So coming to outline of today's lecture, I will talk about parameter estimation for simple univariate linear model. Simple, I told that why we are calling it simple. Anyone again would recall why we are calling it simple? Because you need to know that meaning of simple. Also you need to know the meaning of univariate. Why we are calling a simple linear model? What is meaning of simple? Anyone? Yeah, single attribute. As in short, I will write it as a single attribute, and univariate, that means single response. So that is the approach. Univariate. Bivariate means two response will, trivariate three response. Like it depends upon multivariate and other things. Those are part of multivariate is part of model 4. So we will discuss from there. Then I will talk about few examples, simple example on simple univariate linear model. We will try to do model estimation, parameter estimation or model estimation. Simply we want to estimate a model. That means we are introducing a linear model over that, and that linear model involves parameter. So we want to estimate parameter. There is a non-parametric approach, but that one is complicated one. We will not cover that in this course. Okay, so first coming to parameter estimation. So before going to parameter estimation, I will talk about a general theory of computing parameter for a linear model. I am talking about there is a difference between computing parameter and estimating parameter. Computing means, that means we try to compute parameter from the linear model where we know everything about the data. That means we know that data, complete information about the population. We are having a proper distribution of the data. Then we can compute the parameter. That if suppose that parameter population size happens to be small, in that case definitely it is very easy to come up with distribution of that population, and we can calculate their parameter, or we can compute their parameter of the linear model. Okay, but if that population size is very large, then that computation is not possible. So we are going for estimation, and then that estimation try to estimate parameter, those parameter. It is not giving exact value, it is giving approximate value. Approximation is coming there. That's why you need to talk about error or efficiency or sufficiency and other kind of characterization of one estimator. So here I am talking about computing parameter in a simple linear model. That means we are having distribution of the involved variable in the linear model. So we consider a simple univariate linear model. That means here regression function is expressed as a linear function of the parameter. It is a linear model. Simply we can say that it is a linear model. Why? Because we have taken a linear structure. Linear structure which it is coming function here w naught and w sorry omega naught and omega 1, those are making defining the function. So it is a so you can say that f is characterized by uh, omega naught and omega 1. So f is, that means defined by omega naught and omega 1. How it is defined? It is defined by through, if you put argument over this f, then it becomes omega naught plus omega 1 time x. So that's way knowing x means knowing omega naught and omega 1. In order to compute f means you need to compute omega naught and omega 1. Why? Because x would be given to you. X is the attribute, it would be given to you. So that is the story, and we are here we are taking linear structure. Now we have to apply expectation both side. Then what we are getting, if you apply expectation both side, call this one equation 1. This is the equation or expression 1 or equation 1. If you apply expectation both side, then from the law of iterated expectation, we see that expectation of conditional expectation is equal to expectation of this response variable y. So it is directly coming from law of iterated expectation, LEE in short, I would like to say. Okay, and we are applying expectation both sides. That's why this omega naught is what? It is not involving variable, so it will just omega naught. Expectation of omega naught would be omega naught, and expectation of second term, this omega naught time x, it would be omega naught omega 1 times expectation of x. And from here we can express omega naught in term of like this way. Okay, and here further we try to express this linear model. We will call it expression number 2, where we just see only one parameter omega 1. Through this simplification, we did simplification. It is not like directly we are doing. Again, what we do, uh, we need to multiply the equation 1 with random variable x, multiply with random variable x, and after that take expectation. Then what we are getting, we are getting this expression, and we know that expectation of x time conditional expectation, it is equal to expectation of x into y. That derivation I had already discussed. Call it equation 3. So here we are able to calculate this expectation only in case we know the complete distribution of x. So x will have distribution, some kind of distribution definitely. What would be distribution? That means if x is continuous, then corresponding we know that corresponding probability density function. If f is x is discrete, then we know the corresponding probability mass function. That one is having. That's why we are able to calculate all these expectations. So here we are talking from the population perspective, not we are talking from the sample perspective. So you remember that. That's why I am here. I'm not doing estimation. I'm doing it here computation. Computation word title you might have already seen that it is computing. So that's then we will able to calculate expectation of x square. That means second moment. And further, what we do, we multiply expectation of x both side of this equation, both side of this equation. Then we are getting this equation 4. We are giving name to this equation 4. Now by taking in this equation 3 and equation 4 and recalling the definition of covariance, we can find the expression of omega 1 in term of as a ratio of covariance of x and y uh, and variance of xy. So when you are able to calculate all these, so you need to know the corresponding probability distribution function, and also variance when you will able to calculate when you know the distribution of x. When you are having a complete information, then you are getting exact value of omega 1, and once you are able to calculate the value of omega 1, substitute this into in this equation, that means equation 2, and you will get value of omega naught. So here omega 1 and omega naught, these are not approximate value, these are exact value. So that's where computing word is coming. And to get the exact value, it is very much essential to know the distribution of x and y both. That means distribution of your response variable and also distribution of the attribute. If you know, then you are able to calculate. But in question, this one is the direct problem. If you are computing parameter of a simple univariate model, then it is a direct problem. Here distribution of x and y both are given, and you are calculating the involved parameter. But in general, it is not possible to get distribution of x and y. Why? Because we will have just sample. So from the sample, if just sample is there, we need to estimate the corresponding parameter. So, and hence in that case the problem becomes what? Indirect problem. So I will talk about just we are having a data set of certain sample size. Some certain number of sample is given here, but we don't know the distribution here. Here problem is that we don't know the distribution of x and y. That one is no. So in that case, we will do apply some kind of parameter estimation technique. One technique is calling it method of moments. So what we do, we try to express, we try to find estimation of various moment of the corresponding random variable, because it is not possible to calculate moment of these involved random variable. Why? Because distribution of those random variable is not given, so just sample is given. So from the sample we can do only estimation. So that's why estimation word is coming here. So here I will go further to discuss about the value of the various moment comprised in the formula of the estimator of a regression parameter are unlikely to be known in the absence of sample data. If there is no sample data, then we can't talk about estimation of those things or estimator of that way. And simply someone is saying that if suppose we are having a single data set, single data, sample data, from there just we can get estimate. We can't get estimator. Yeah, how you can get estimator? Because you have to take sample of several sample of the same size. So just one sample you are having, then how you can get several sample? You can get several sample by doing some kind of sample resampling technique. That means either yeah, there is a facility to take other samples of the same size from the source. You go, if it is not possible, do resampling. That resampling, that means bootstrapping kind of things, or some kind of permutation you can do among the sample itself. Due to that you can get various resampled data, and with respect to each sample resample data, you are getting estimate, and those estimate is making a several observation of the estimator, and hence you are getting an estimator. So that is the source. That means from the single sample data you can create estimator. How? By doing resampling. So consider a sample of n observation on x, it is given, x and y it is given. Y response is also that label is also essential to infer something. That's way. So x data, x and y both are making into the data set. So we are having n samples. So x1 y1 x2 y2 xn y1. You can remember that these are the fixed number, these are not random variable, these are the fixed number. First data point, second data point, and nth data point. That means n number of data point is given to us. That means sample of size n given to us. Then what we do, we apply empirical approach or sample moment approach to calculate, to estimate parameter. To estimate parameter, we do estimation here. So estimate parameter, how we do? So first because we don't know the distribution of x, and the in the last slide we had already seen that the derivation of that parameter involves expectation of x expectation of y, and if distribution is not given, then we can't calculate these things. So what we do, in place of expectation of x and expectation of y, from this sample we will calculate estimate sample mean. This is the sample mean of attribute, this is the sample mean of response, and this is what we are defining sample uh, variance of attribute. Likewise, you can define sample variance of uh, response as well. But in the last definition, you might have already seen that omega 1 was expressed as a ratio of covariance and what we call variance of x, that means attribute. So that's why we could, there was no direct involvement of variance of y, there was not. So that's why I'm not defining here sample variance of y here, just I'm defining it sample variance of x. This is the sample variance of x. So if I talk about this sample variance, whether this sample variance is bias or unbiased estimator of variance of x, anyone may comment over this. I have defined sample variance as uh, average 1 by n times summation of square deviation by sample mean. So tell me whether this sample variance is a bias or unbiased estimator of the variance of x. Anyone? Anyone would like to say that anything? That means if you try to find expectation of the corresponding estimator of variance as a square through this definition, then what would be expectation of this would be equal to what actual variance, the population variance of x or not, it would be equal or not. If it is unbiased, then it would be equal. If it is not unbiased, that means if it is biased, then it would be not equal to. Then just recall few previous lectures I had already discussed. So if you are defining if you are taking ratio 1 by n, then with this definition of sample variance, it is not a unbiased estimator of variance, it is a bias estimator. That's why expectation of s square, it would be not equal to sigma square with respect to s. I'm talking about with respect to attribute x, so it would be not. So this one is a bias estimator. So generally in least square estimator, for the estimation of variance we are having bias estimator, but mean estimator is what, unbiased estimator. Likewise also we are defining covariance, this is the sample covariance. So we are defining like this way, and sample covariance simply we can define in the similar fashion like this way, and this one is the simplified form. I'm taking it simplified form. You can define it like this way: xi, mean deviation of x by sample mean, times mean deviation of y with sample mean of y, sample mean of y. So you can define covariance, sample covariance by this way, and you have to divide it by 1 by n. Again 1 by n is coming, so this one would be what, uh, bias estimator of biased estimator of what we call it, covariance it will give. It is not giving unbiased estimator. And further if you simplify, just to do this summation, yeah, I is running from the sample size is what, n 1 to n. So n observation we have taken, so that's why it is running from 1 to n. So if you simplify this one, then this will take very simple form. So what is this one? If you try to observe, it is what it is talking about, second moment kind of a structure it is taking, second moment type of a structure. What is this one? This one is a square of the first moment, but estimated moment, it is not exact moment, it is estimated. All these are estimated, estimation thing are coming with respect to sample, it is coming. Okay, so the we can find here, we can't compute omega naught and omega 1 from this sample only, but we can estimate the value of omega 1, omega naught and omega 1. So what are those? The estimate of omega naught and omega 1, that we denote it by hat or cap. Omega hat naught, omega naught hat, that is what, y naught minus omega 1 hat or hat or cap also you can say that both are same. So omega 1 cap time x bar, that sample mean of x, and this one is the sample mean of y, that you can calculate from the sample. Okay, and omega 1 is what it is, ratio of this, ratio of product of mean deviation, sum of product of mean deviation of x and y divided by that this quadratic term. And yes, it is I varies from 1 to n, that means that sample size what you have taken. So this one is a feasible problem. You can easily estimate this value omega, that you can get one estimate of omega naught and another estimate of omega 1 you can get. So you are getting estimate from the sample, so that's why these are the estimator. So once you are having estimated value of omega naught and omega 1, then you have to talk about various properties of criterion of those estimate, so that efficiency and error all you have to talk about a lot. So it is one technique I discuss it here. So further, if you perform estimate, then in that process of estimation you are getting estimator with of a particular parameter. Then what you have to discuss, that means estimator is what it is, you are taking sample of what sample of various sample of the same size. Then it that in that case here omega naught I will write it not sign I had already taken. So okay not I will put it up, and here in suffix, or better in the I will put n over here. So omega naught we are cap we are getting with respect to one sample, but we are having various sample of the same size. So that means we are getting a sequence of sample, we are getting a sequence of sample. So if you are getting or capital N, you can say that. Okay, right, leave it. And likewise also you will get several uh, estimator of omega 1, that also we are calling it n. So in long run, when you are going to increase the samples, number of samples of particular size, where does it will go? It becomes a sequence with respect to all those number of sequence, so it will converge to omega naught. So you are talking about convergence of sequence when n is, when you are taking various sample of the same size. Okay, when you are taking various sample of the same size, that means n tends to infinity. Okay, so that you are talking about asymptotic nature. Okay, so it will converge to omega 1 cap, it will converge to omega 1 we are when you are taking various sample. So if simply I ask, what about the convergence of sequence, this convergence of sequence, is it similar to what we had already discussed in math 1, that in math 1 you might have already seen convergence of sequence. That means if you're defining convergence, an is a sequence, and if you're defining convergence of a sequence, then you can express it with the help of uh, epsilon and definition. What does it say? For every epsilon, positive epsilon, there exists a fixed natural number n naught, you can call it n naught, such that you can say that ultimately uh, an, that member of the sequence, is very close to a, very close to that epsilon, close to a, for all the n which are greater than equal to n naught. So this is the epsilon and definition of convergence of sequence that you had already seen in math 1. But whether this convergence and what we are talking about convergence of estimator to what the parameter, both are same. It is not like both are same, because here this one is deterministic convergence. Here there is no involvement of randomness. Here randomness is not involved. But when we talk about estimator, randomness is coming there, because estimator is a random variable. So that convergence is a little bit complicated than this simple deterministic convergence. So we will talk about convergence of estimator to the corresponding parameter. How we will talk about in statistically. That means there would be some kind of distribution of probability will be involved. That's why we are defining convergence in probability. So we talk like this way. So in many of the circumstances under which the data are liable to be generated, the sample moment are expressed to converge to the true moment of the bivariate. That means if you're defining x bar, the sample mean, we are asking to converge this to uh, the true moment, that means our population moment, that one is expectation of x. If you are asking to converge to this one, then we are taking various sample of the same size, and we are talking about convergence. That means in long run, in various sample, does it converge to the expectation of x? Likewise, this sample mean from the sample, given sample, does it converge to expectation of y? Also here we will talk about like this way. Does it converge? Like, so this convergence is not normal convergence, that ordinary convergence what we had already seen in math 1. It is something more than that, thereby causing the estimator of the parameter to converge likewise the to the to true values or true parameter. So the concept of ordinary convergence is not appropriate to the case of a stochastic sequence. Why? These are what? Estimator. These are involving estimator. So that's why these convergences are not ordinary convergence. These are stochastic in nature, because some randomness, stochastic, or that means randomness is there. So stochastic is nature, and hence we can say that what is this sequence is what it is, a probabilistic sequence or a stochastic sequence, we can say that. So we are getting this sequence as a sequence of estimates, so, and hence randomness is there, or these are stochastic in nature or random in nature, simply I would like to say that. So we need to define convergence of a stochastic sequence. How? For no matter how many observation we are having have been incorporated in the estimate a, and suppose a n is the estimate of some parameter a. I just remove that cap, so it is a estimate. What it is a estimate of a, we are having a parameter a, and for various observation of size n, we come up with uh, a sequence of estimator an. There remain a possibility that subsequently an aberrant observation yn will draw the estimate, and an, this one would be, this is the estimate, nth member of the estimate, you can say that, beyond the bound of plus minus epsilon. There might be one observation yn, even observation we are calling it xn, will also data set, simply you can say that, that will that will, with respect to that, if you try to calculate one value of the estimator of this an, that value may not fall in the epsilon ball of a. You can also, in math 1 you might have already seen the epsilon ball of a. So may not fall in, but probabilistically may fall there in that interval. So we will talk probabilistic convergence like this way. So a sequence of random variable an is said to converge weakly in probability to a limit a if for any epsilon there exists a limit probability, you can read it like limit probability, such that we say that the probability that in long run, the probability that an is epsilon away from the true parameter a is 0. The probability that in long run an is epsilon away from the true parameter is 0. This is convergence in probability. And same thing you can talk in alternative way, that means probability that an is within epsilon ball of a is equal to 1. It is meaning of convergence in probability within epsilon ball of a with probability 1 in long run. When n tends to infinity, that means long run. within epsilon ball of, what is the probability that within epsilon, or what is meaning of convergence in probability? That means within epsilon ball of A with probability 1. We can't leave here probability term. Probability term is coming here, so that's why we call it, it is stochastic convergence, or convergence of a stochastic sequence, or a stochastic convergence. So estimator is always a stochastic sequence. That is, by increasing the size of sample, we can make it virtually certain that an will fall within epsilon ball of A will fall. Conventionally, we describe A as the probabilistic limit of an. It is not an ordinary limit, it is a very specific limit that we are calling it probabilistic limit of an. An happens to be an estimator. The virtue of this definition of convergence is that it does not presuppose it does not presuppose that the random variable an has a finite variance or even a finite mean. Okay, suppose if that is the situation, suppose it is not there is no information about finite variance and finite mean of the estimator an. There is no suppose we are having an which is having a finite variance or finite variance, finite mean, or those kind of things. Then the concept of mean square convergence can be employed as a sequence of random variable an, and is in that case we convergency we are calling it mean square convergence, and we define like this way. So in place of here it is dealing probability, but here if we suppose finite moments are given, that means finite that mean is given and finite variance is given for the particular estimation, then you can talk about convergence in expectation or mean square convergence. That means define first a square, and after that find expectation, and after that talk about convergency. So here it is calling it about mean of what a square convergence, mean square. Simply in short you can call it mean square convergence. So can you give any example which are having mean square convergence? Anyone would like to give an example? I had already discussed in estimation, so few estimator were there which were having mean square convergence. Anyone would like to give answer? What are those estimator which are having mean square convergence? Anyone? Are you getting my question or not? What I am asking? I am asking here that do you know any estimator which is having mean square estimator, mean square convergence? Anyone would like to answer it? Aditi, do you know what kind of estimator is that one? Okay, Kalpjit, do you have any idea? Yeah, I am talking about mean square convergence. So what estimator is having mean square convergence? I had discussed various estimator in during estimation process. Estimator of mean, estimator of variance. So tell me, anyone estimator which is having mean square convergence? No idea. If you take estimator of mean, that sample mean, and keep on varying that sample size, then you will get estimator of mean, and that estimator of mean is having variance. What is that variance? So variance, I had defined that if you are taking sample mean, how we define sample mean? We define as we sum the n observation and divide it by the sample size n. So this one was the definition of sample mean, and it is giving one estimator one estimator. Okay, so if you try to find mean of this one or variance of this one, mean, what would be mean of this sample estimator? What is the estimator of sample mean? What would be mean of this one? Mean of this one would be true mean of the variable that we are calling it mu, or you can call it expectation of x. There is no issue. Expectation of x, if you know the distribution. If you don't know the distribution, you can't calculate expectation of x. In short, simply we are calling it mu. So this one is what? It is a finite number. So it is having a this sample mean is having a finite mean. This estimator is having a finite mean. Again, what is the variance? Variance of sample estimator of sample mean. What was the variance? Anyone? Variance was sigma square by n. So for each n, definitely it is a what? It is a finite variance. That the estimator of sample mean is having finite mean and finite variance, and hence we can say that the estimator of sample mean is having mean square convergence. So that is the example I would like to say, that mean square convergence. If you are, sometime it may possible that few estimator may not have finite variance or finite mean, that means expectation. In that case, you can go for convergence in probability. So convergence in probability is covering larger class of estimator, and mean square convergence is covering a smaller class. So if you take this, this is bigger, this covering all the estimator which are having convergence in probability, then in this within this we will get all the estimator which are having mean square convergence, mean square convergence, MSC. And here bigger class we are calling it convergence in probability. So this is the bigger class. So and here sample estimator of sample mean is coming here in the smaller class. And this one is much easier to deal with. Always you will see that calculation of expectation is much easier than calculation of probability. It is much easier. So that's where this looks easier concept. So that's where estimator of sample mean is little bit easier. Also likewise, you can go for estimator of variance as well. Just take as a homework, try to verify whether estimator of variance is a having that mean square convergence or not. So I will talk about example. I have taken few interesting kind of example. So first example I am talking about signal estimation. So we will try to, so there would be some noisy observation. We are having noisy observation. That noisy observation involve two things. One is signal, another one is noise. So we are not worrying about noise much. We have to estimate only signal. So same problem you can put in another way. If someone is having noisy observation, that person will do focus on denoising. That means that person is focusing on to remove that noise. So in order to remove the noise, what you will have? Ultimately you will have the signal only. So another problem, same problem, the estimation of signal equivalently you can do through another approach, that we are calling it a denoising approach. So same problem you can solve it through two different way. One we are calling it signal estimation, another we are calling it denoising. So denoising focus on noise. That means definitely some kind of noise is having some kind of distribution. You will proceed with that, and after that you will apply denoising. Like I had already performed denoising of what images, few images in one of the tutorial I had already discussed about. And also you can go further, you can talk about filtering process. You have to filter out the noise. So filtering, so one of the important technique that we are calling it Kalman filter. Also you can go all those things. Later we'll discuss all those. So here right now I'm talking about, I'm not talking about denoising, I'm talking about estimation of signal estimation through linear model. So how we can do that? So consider we are having a noisy observation x is the noisy observation. So you can, in short, you can write it noisy observation. We observe this noise. So this x is containing two things. One component we are calling it, it is what, you can call it, here this word is what, it is not e, this word is not h. All these are coming from capital Greek letter. It is this Greek letter of what we call it, capital eta. This h is capital eta. H, it looks like h, but it is capital eta. And I have taken capital in sense that random variable we always denote with capital letters. That's why I have taken. I might have taken a small letter, there is no issue. That may also may represent a random variable. Just we have to change our convention. And this one is the capital chi. A small chi, generally we denote it by like this way. This is a small chi, and this, when you observe this kind of thing, all these are Greek letter. This one is denoting capital chi, in order to talk it that signal, representation of signal. And x is what, English alphabet, you know that. So suppose x is an observed random variable which combines a signal component, that we chi, and a noise component eta. Anyone, anyone would like to ask any question? No. Okay, I will go further. So imagine that the two component, that means signal component and noise component, both will have different source. Signal is coming from something else, noise is coming from something else. So that's way, in general, we take assumption that signal is independent of noise, or uncorrelated. Signal and noise both are uncorrelated to each other. So this, what is meaning of uncorrelated? They are having zero covariance. Covariance is zero. And further, our condition is given that the variance of variability measure of the signal is given. That one is sigma square chi, with respect to chi sigma square, and variance of eta, that noise, is given sigma square h. So different variants are given. So what is our problem here? Here problem is we have to detect the signal from this observation x. So one estimation technique, there are various estimation technique. Here we will apply first least square estimation technique. Through least square estimation, we will try to estimate the value of this chi from observation x. Okay, that is here job. So using the above derivation, that derivation of linear model what I had discussed, that means what derivation, what was the derivation? Derivation was like this way. Omega naught was what, defined as expectation of y response variable, or observation, what you call it, times omega 1 expectation of x. This one is the computation. We are talking about computation. And omega 1 was what? If you know the distribution, then it is very nice to compute all these linear. Omega 1 was what? It was ratio of covariance of the attribute x and observation or response y. Response y divided by also x, also you can call it observation x. In that case it was observation divided by variance of observation x. So this one was the story with respect to linear model regarding computation of the parameter of linear model. Same here, this one is also a linear model. So we get the expression of signal condition upon observation as follows. So what, we are able to observe x here, that's way, and we want to detect estimate signal, that chi. We don't have facility of distribution of this chi. This chi, we don't have facility of this one. So by condition upon the observation x, we are trying to find conditional expectation of eta, sorry, chi given x, it is what? It is, you can express it like this way. So also one more thing, I had written it like this way. One expression you might have already seen, that expectation of y given x. One derivation I had discussed from the linear model. It was what? Expectation of x first, actually we are going to estimate here y. So expectation of y. Anyone is having any question? Plus omega 1 times this one. Omega 1 is what? Covariance. That when we had substituted this value in the linear model. So if you substitute value of linear model, value of omega naught in the linear model, so what you observe? Okay, it is already beyond 45 minutes, so I will cover this thing in later class. Okay, regarding attendance, just put there in the comment.